Okay. All right, so our function again was y equals e to the x. Our differential equation or derivative was dy dx is equal to y. The first point that we wanted to use was 0, 1, and we got the equation for the tangent line through that point. So I'll call it tangent line number 1. Our equation was y equals x plus 1. Since we're letting delta x be 1, we're finding it at 1, 2, 3, and 4, I'm going to put the number 1 in for x, and that's going to give me the point 1, comma 2. So I'll just say that point is there, 1, comma 2. So this is 1 on the x-axis, this is 2 on the x-axis, 3, and then finally 4. All right, so plugging 1 in for x, we get y equals 2. Now y is 2, so the slope is 2. So for our second tangent line, we'll call it tangent number 2, we got the equation to be y equals 2x. We want x to be 2 because we want our delta x to be 1, so putting 2 in, we get 4 for our y value. So we're going over 1 and up 2, or we're getting 4. And that gives me the point, let's say it's about there, 2, comma 4. And the second tangent line then is in here. Now the third tangent line, well, since I want x to be 2 and I get y to be 4, I now know the slope of my third tangent line is 4. So for tangent line number 3, y would equal 4x minus 4. So from that point, I'm going to go up 4 and over 1. So I'll say that's approximately 3, comma 8. And now my third tangent line is here. Okay. Finally, when x is 3, putting 3 in for x, we get 8 for our slope. So we get y to equal, so I'll call this tangent line 4. The y was equal to, putting 3 in there, we got 8, so the slope is 8 now, because again, the derivative is equal to the slope. So 8 times x minus 16 was the equation of the tangent line 4. So we could go up 8 over 1, and that would put me here at 4, comma 16. Or if you were to replace x with 4 here, you would get y to be 16. So our fourth tangent line would be right in there. Hopefully what you can see is the tangent lines are approximating the curve of the function. Of course, the further out I go, the more discrepancy there is between the approximate value of 16 and the actual value of e to the fourth. But imagine if I had made my increments of x's smaller, that would have given me shorter segments in here, and they would have better approximated the actual value. That's called Euler's method.